So knowing that a chemical process will proceed or not doesn't tell you everything about it. All right. One of the things that we often want to know is the speed with which that occurs. All right. And by speed, that is often described as being the rate of the reaction. All right. So the study of this is called chemical kinetics. And to give a little bit of an introduction to this, I'm just going to start with a very simple example. Let's pretend that we're in a factory and we're making bicycles, and we know that two wheels can be combined with one frame to make a bicycle. All right. And we know that depending on how efficient your factory is, the rate at which the bicycles can be produced can either be slow or fast. All right. We might just be able to make 2 bicycles per hour. But in another factory, they might be able to make 20 bicycles per hour. All right. So one thing about measuring this rate of this process is that we need to be able to focus on something that is measurable. All right. So it seems obvious that if you're talking about bicycles, yeah, all we have to do is count either the number of bicycles that are coming off the assembly line, or we could count, for example, how fast the pile of wheels that we're using is disappearing. And that would give us an indication of how fast this is occurring. But remember, if we're doing this with a chemical reaction, things aren't as easily countable as if we were dealing with objects in the real world. All right. So for chemistry, we need to make sure that we're focusing on something that is measurable. And so just a quick overview, and we'll talk more about this later. What are some things that would be measurable about a chemical reaction that might tell you something about the speed of reaction? All right. Well, what if you have one of your products in the chemical reaction as a gas? All right. Well, you could put a balloon over the top of your flask, and the volume of the gas that's produced would be an indication of the amount of that material present, and you can measure how much is generated over time. Another thing that you could do that would be measurable is if one of your products, either one of your reactants or your products, has a color. You could observe a color change. All right. There's a machine called a spectrophotometer that would allow you to measure that. When we get to acids and bases, you'll see how sometimes pH, measuring the pH or the relative acidity of something, would give you an indication of that. And also there are reactions where heat is generated whenever the reaction occurs. All right. So we can measure the heat production. All right. These things might seem obvious, but keep in mind, a lot of times when you're doing chemical reaction, you have, for example, colorless solid reagents, and you might have colorless liquid product. All right. And in some cases like that, it's not that easy to tell how fast things are either disappearing or appearing, because you just don't have a visual any way to measure it. All right, so keep in mind we need to focus on something that's measurable. Okay, so let's go back to pretending that we want to measure how fast this process of the production of bikes is occurring. All right, well, there's a couple ways that we could do this. All right, so let's say that we were in the factory, and the only thing that we could see is the bikes coming off the assembly line. All right, we couldn't see the piles of wheels disappearing, or we couldn't see the piles of frames disappearing, but we could see this. All right, that would be one way of measuring it. So that would be measuring the appearance of a product. All right. Alternatively, let's say that we couldn't see the bikes coming off the assembly line. If we could focus our attention on how fast the wheels are disappearing from that pile of wheels in the factory, that would also give us an indication of how fast this process was occurring. All right. So I mentioned appearance or disappearance. What we would actually be doing is measuring the rate of the change in the amount of the amounts of these things over time. All right. So remember what change is. Change is always measured as however much you have in the end. So this little part right here stands for for final. I is for initial. So it's, change is always final minus initial. So if we wanted to measure the rate of change in the amount of wheels, it would be the final amount of wheels minus the initial amount of wheels divided by the time. All right. If we wanted to measure the change in the bikes, that would be if we were focusing on how many bikes were coming off, it would be final amount of bikes minus initial over time. All right. Well, the thing about this is that if we're focusing on the wheels, if we're focusing on a reactant, what happens to the amount of a reactant over time? All right. If this process is occurring, all right, in the end, let's say that in the beginning we got 20 wheels, we got 10 frames, and in the beginning we have 0 bikes. All right. In the end, we're going to use up all our wheels, all our frames, and we'll be left with 10 bikes. All right. Well, the final amount of wheels in the end, you'll see we have 0 wheels. All right. We're going to subtract 20. That's our beginning, and it happened. Let's say that this happened over 1 hour. All right. So the rate of change for wheels is minus 20 wheels per hour, and the reason that it's minus is that you're for wheels you are losing the number of wheels over time. All right. If we did the same thing for bikes, all right, the big difference is that bikes are increasing over time when this process is occurring. All right. So we end up getting a change of positive 10 bikes per hour. All right. So the problem with measuring things this way is that one person might say, hey, we've got negative 20 wheels per hour. The other person is saying positive 10 bikes per hour. But the thing is, they're actually measuring the rate of the exact same process. The exact same event, all right, so we'll just say a reaction event is whenever 2 wheels combine with 1 frame to make 1 bike. Every time that happens, you're going to see an increase of 1 in the amount of bikes, but you're going to see a decrease of 2 in the amount of wheels, even though it's the exact same event that is occurring. All right. So the thing is, we want to be able to say, give one number, one expression for how fast this process is occurring. We shouldn't get different numbers and different signs just because in one case I chose to use the production of a product as my way of measuring it, and in another case I used disappearance of a starting material. So the way that this has gone about is that if you're talking about a reactant, and this might look kind of complicated, but it's actually fairly simple. The way that we're going to do this is we're going to say that the rate of the process is negative. The rate is going to be the negative 1 over the reaction coefficient times the change in the number of reactants divided by time. All right. So for products, it's going to be, the rate is going to be positive 1 over the coefficient times the change in the number of products over time. All right. So why do we, first of all, what's the purpose of this negative? All right. So remember, if you are focusing on a reactant, we're talking about something that's going down over time. So even if the process is going forward, your change in the amounts of the stuff on the left is going down. So to represent, signify that this is part of a forward process, we have to make that negative, so that the negative of the negative change in that ends up being a positive number. All right. So what about this part right here with the coefficient? All right. So remember, for every 1 time this event occurs, all right, for every 1 time this event occurs, we're going to lose 2 of these. All right. So what we want to have is the rate is essentially a measure of how fast the reaction event is occurring, not necessarily how fast each individual one of the reactants or products is being consumed. So by doing that, so since the coefficient for wheels is 2, I'm going to put that right here in the expression. And when we do this, we end up calculating that that would be positive 10 reaction units per hour. All right. So if we lost 20, hopefully this makes sense. If we lost 20 wheels per hour, what that would mean is that we had this event of this thing working 10 times per hour. All right, and notice I say 10 times per hour. That means positive 10 times per hour. All right. Alternatively, so we make one bike. All right, so if we put this bar right here would be 1 over 1. And notice that this is positive. All right, and the reason that this is positive is that the change in the number, if this is a forward process right here, the change of the product is going up over time. So that's a positive change. So we don't need to do any changing of the sign there. So notice that no matter which way you do it, you end up getting the exact same rate. All right, positive 10 reaction units per hour. Okay, so notice that this a reaction rate can also be represented graphically, and we'll do a little bit more, give a little bit more attention to graphs a little bit later. But what we're going to do first is we're going to just have an XY set of axes here, and we're going to measure the concentration of a reactant on the y-axis, and we're going to measure time on the x-axis. All right, and focus on this curve right here. So the actual graph is going to be this curve that comes down like this. All right, so one thing about rate, one way that we can figure out the rate of the reaction at any given point in time is if we draw a tangent line to the graph. All right, and where that tangent line hits the graph, at that point in time, the slope of that tangent line would show the instantaneous rate at that time. All right, so notice that over the course of this reaction, the reaction is actually slowing down over time. All right, so the reason that this works is if you draw that tangent line and then you draw a triangle there, at that given point in time, this side of the triangle right here would represent the change in A, and this side right here would represent the change in time. And just using rise over run, that would tell you essentially change in concentration divided by change in time, and that's going to be the rate.